Okay, I'm going to try and explain a little bit about these SHM graphs and equations. So I'm going to start by looking at displacement. So we've got x up here and then we've got time along the bottom. And then I'm breaking it up into 90 degrees, 180, 270 and 360. So that's a complete circle and therefore one complete oscillation. And I've also put the radians underneath, so we know that 2 pi radians is a full circle. So we've got half pi, pi, 1.5 pi and then 2 pi, and that represents one oscillation. So if I imagine I've got something like a pendulum, then this is the equilibrium position here. I've pulled the pendulum back to start, and at the moment it's here, the x here, this is the displacement. The maximum displacement will be the amplitude of the oscillation. So I'm going to call that A. So we know it starts off at A. So when I start off my oscillation over here on the graph, at 0, then I've got my maximum amplitude. Okay, and that's where the graph starts. As the pendulum comes through the equilibrium point, then the displacement becomes 0. As it moves to the other side over here, then it will also become amplitude, but it's going to be in the other direction. So I need to go down here on the graph, so it's negative in the other direction. Then we come back through equilibrium, which means we come back to 0, and then finally we get back to our starting point, which we back up here. And I'm going to attempt to draw a nice, neat curve, so we end up with something that looks a little bit like that. Now, in terms of whether this is a sine or cosine graph, if we go to our calculator and we were to have a look at the cosine of 0, whether it's degrees or radians, I would end up with the value of 1. So in effect, it's going to start up here. If I then look at the cosine of 90 degrees or pi by 2, I'm going to end up with 0. The cosine of 180 degrees or pi will give me -1, and the cosine of 270 will give me 0 again. So you can see that this is the shape of a cosine graph, not a sine graph, even though it's sinusoidal. So I start off with x is equal to a cos omega t, and in the other video that I've done, I've explained a little bit more about why it's a cos omega t, and I've related it to a circle. So it's quite useful at this point then to compare what happens with velocity. So if I'm looking at velocity and I go back to my diagram, then I'm no longer looking at x and I'm looking at velocity. And the thing to think about is when I pull it out at this point here, it's going to be stationary. It's not going to start moving until I release it. So at the point that I release it, the velocity here is going to be stationary. Then it's going to accelerate to the equilibrium point. Then it will start to slow down again until it reaches rest again up here before it changes direction and comes back through equilibrium. So my graph is going to take a different shape to reflect that. So let's just sharpen that image a little bit. If I then draw the same graph, but I now consider what happens with velocity, then again I'm going to have the same sort of axes. Time's going to come across here, but I've now got velocity. I'm still interested in the same points on the graph, so I've got 0, pi by 2, pi, 3 pi by 2 and 2 pi. So going back to what we know is going to happen on my pendulum, we're starting off with a velocity of 0 because it's starting stationary. We then know that it's going to accelerate until it gets to the equilibrium point, and that's the fastest point it's going at. It's going to come up here. We then get to halfway through the oscillation. It's going to go back to 0 because it's going to stop here, and then it will change direction. The velocity will then get to the maximum again, but in the other direction. So down here, and then finally come back to rest up here before it changes direction again. So now what I've got is a sine curve. Okay, and again we know that the sine of 0 is equal to 0. The sine of 90 or the sine of pi by 2 is going to equal 1, and so on. So sine of 180 is also equal to 0, and the sine of 270 or here is going to be -1. So what I've got is a sine graph. So If I try and come back a little bit and have a look at those two graphs together, then what you can see is that they're both sinusoidal, but as you've mentioned in your work, the first one is cosine and the second one is sine. So I'm going to end up with the velocity is equal to minus a omega sine omega t. And again, in the other SHM video I've got, it explains why we get these two particular equations. But the key thing is, this is cosine and this is sine. The last one then would be acceleration. Now, normally, if I'm teaching this to a class, I put all of these three on one page. I'm just going to do that now and show you what that looks like. Let's get a fresh page. So if I now consider all of those three graphs together, if I start at the top with displacement x, then we know that that's going to be a cosine. So the reason I'm doing them all in one go is I can then put the quarters in here. That's my pi by 2, that's pi, 3 pi by 2, and then 2 pi at the end there. So I can label these at the top. So I'm going to have pi by 2, pi, 3 pi by 2, and 2 pi. So if we looked at what happened with our displacement, then we had this sort of graph going on. So that's my cosine. We then come down and have a look at what happens with velocity. And if I look at velocity, we saw we had a sinusoidal graph, like so. And so the last one to look at then is acceleration. Going back to my pendulum then, so at this point here, when I hold the pendulum at this point here, then when I release it, it's a little bit like we talk about the parachutist jumping out the plane. At that point, we've got gravity pulling the pendulum down, so there's no other force acting. So this is the maximum resultant force, which is also therefore the maximum acceleration. At this point, when we get here, this is actually slowing down now, and at this point, acceleration will be 0. Then it's going to continue up to the other side, and at this point it comes to a halt, but the acceleration is now acting in the other direction, but it's maximum acceleration, and then acceleration is 0 again in the middle. So when I draw my acceleration graph down here, move this down a little bit so you can see, I'm going to end up with maximum acceleration, 0 in the middle, maximum, 0, and maximum. So you'll see that I get a cosine graph again for acceleration. And that means that I end up with these three equations that match these three graphs. So I've got x equals a cos omega t, v is equal to minus a omega sine omega t, and the acceleration is equal to minus a omega squared cos omega t. So again, now these three equations reflect the shapes of the three graphs. And you'll notice here that if we are saying that displacement x is in this direction, then the velocity is going in the opposite direction, as is the acceleration, as is the restoring force. So we end up with this idea that the acceleration is proportional to x, but it's in the opposite direction. So I hope that helps a bit.